Hello, everybody. My name is Lucas Sanchez, and today we're going to be looking at a problem that we've seen a few times this semester, in which we have a tank, and we have some flow rate into the tank, and then we relate the flow rate out of the tank into the height of the tank. So let's back here. Hello, everybody. My name is Lucas Sanchez, and today we'll be revisiting a problem that we've seen a few times this semester now, in which we have a tank of a given initial height of liquid in the tank, and we have a flow rate coming in, some flow rate Q coming into the tank, and we have some flow rate leaving the tank that relates to the height of the liquid level in the tank. And those two are at a steady state initially, in which we have the height of the tank at a set value, and it's not changing. Initially, we used a differential equation solver on Python to simulate the height of the tank over time. Today we're going to investigate a new method in which we look into deviation variables and transfer functions to investigate this change in height. So let's draw the situation to kind of give everybody a refresher of what we'll be working with. We have the tank here. We have some flow rate Q coming in. We have this hole at the bottom here. Out comes some flow rate. And we know that the flow rate out is the A times square root of 2GH. And for our terms, we're going to simplify this as alpha, and alpha will be equal to A times the square root of 2G. So the flow rate out will be equal to alpha times H to the 1/2. So when we set up our mass balance, we take the area of this cross-sectional area of this tank, AC times the change in height over time will be equal to the flow rate coming in minus the flow rate coming out, which is alpha H to the 1/2. Now, if we want to be able to use this expression in terms of the transfer function, we need to linearize it, because in order to obtain the transfer function, we're going to need to take we're going to have to do the Laplace transforms of the function, and in order to do that, we need to have a linear function. So how are we going to linearize this term h to the 1/2, because that's our nonlinear term here? We're going to use a Taylor series expansion and expand it upon the initial steady state value of h bar, and that'll allow us to obtain a nice value or a nice expression for a linear expression in terms of the deviation variables that we'll then be able to use Laplace transforms and obtain the transfer function that we're looking for. So let's go ahead and do so. So AC dH dt will be equal to Qn. And now for the Taylor series expansion, we're going to expand it upon h bar. So let's just say h bar and q bar. Those are both initial. And then initial steady state. So initial steady state. So we're going to linearize. That'll be alpha times square root of h bar minus 1/2 square root of h bar. And then we multiply this by h minus h bar. So this is just the initial value of the function minus the derivative of the function times how much it deviates from the initial value. And then we can further simplify by then looking at the function at its initial steady state, everything in terms of that. So 0, we know at the initial state we have a steady state, so the level in the tank's not changing, so dH dt is 0, so the whole cycle is 0. And we have 0 is equal to Q bar minus alpha, still be h bar minus 1/2 h bar minus h bar. And now we take the difference of these two functions, or two expressions here, and we obtain AC dH dt will be equal to Qn minus Qn bar minus, these terms will cancel out. Sorry, this should be plus here. So it'll be minus alpha over 2 square root h bar. And it'd be h minus h bar. So when we have these terms q in minus q bar in, that's equal to q prime. And then we'll have h minus h bar. That's going to be equal to h prime. So when we look at these values with respect to the initial value, these are our deviation variables now, q bar, or q prime and h prime. So we're looking at them with respect to the initial values, the bar values. So those are our deviation variables. So now we're going to go and attempt to set this function, ac dh dt, in terms of these deviation variables. So sub in the values, ac dh dt is equal to q prime minus alpha over 2 square root of h bar h prime. And then we can even determine or set this equal to, we can have, h prime equals h minus h bar. So when we take the derivative of the function, dh dt simply equal to, this is constant value, so it's just equal to dh dt. So we can plug dh prime dt in here. So now that we have everything in terms of deviation variables, and it's a linear expression, everything's to the first power, we can now express it in terms of the Laplacian domain. So we say AC dh dt will express as h prime will be equal to q minus alpha over 2 h bar, and this will be h prime again. So we simply move it over to the other side, ACH plus alpha over 2 square root of h bar prime, is equal to q. And then we sub some things out, so h will be equal to AC plus alpha 2 square root of h bar, and that's equal to q. So we'll have h is equal to 1 over AC plus alpha over 2 square root of h times q. So this flow rate is one of our variables we're looking at, and this here is the transfer function. So h, height, and the flow rate are our deviation variables. This is the transfer function, and then when we change this value of q, we multiply the transfer function to see its impact on the height there. So those are our two deviation variables. And like I said, we initially typically just take this expression and use solve IVP to investigate the change in height in the tank over time. But in this case, we're going to try something new, and we're going to use the inverse Laplace transform to get a numerical expression that we can use to look at the change in height of the tank over time. So this expression here is similar to oh no, I forgot something. I forgot the S. That's a big deal here. Okay, now we're good. The Laplace transform of a derivative is a all right. So it's similar to the form of a function, just equal to k over, or we'll just, similar to the function k tau s plus 1. So we want to get that form, we simply have to divide the bottom by alpha over 2 square root of h bar. So we'll do that, and we multiply the rest as well. So it'll be h is equal to 2 square root of h over alpha over 2 square root of h alpha times a c s plus 1. So here will be our k value, and then here is our tau value, h, and that's multiplied by some value of q. And we're gonna say q is equal to some value a over s. That's the inverse Laplace transform of this function. No, no, never mind. Simplicity, I'm going to put it as k tau s plus 1 a over s. So now we're going to use the inverse Laplace transform and use this relationship of a over k. So if we have a value of 1 over tau s plus 1, the Laplace inverse Laplace transform is 1 minus e to the power of negative t over tau, I believe. So when we have the value of ka, we have h prime equal to ka 1 minus e to the power of negative t over tau. And as we know, h prime is equal to h minus h bar. So it's h bar plus ka 1 minus e to the negative t over tau. So this is an expression here that we'll now use to numerically solve and then plot the change in the height of the tank over time. So we'll do both the analytical solution that we usually use, and then we'll also do this numerical solution now that we have to solve it on Python. So let's head over there and take a look at what it looks like. All right, so we're over here in Python now. Let's start coding this out. Let's import the necessary libraries that we usually use. So import numpy. For the libraries there, now let's go ahead and define the parameters that we're given in this problem statement right here, actually. So we have a tank, and we're going to say the initial but the cross-sectional area for this constant will be 2 meters squared. The initial flow rate in will be equal to 0.5 meters cubed per second. What else we need to assume? Some alpha value, because we said that square root of 2g, square root of 2g times the area of the whole is our alpha value. So alpha, in this case, will be 0.5. Then we have to define our initial height, which we can use 0 will be equal to qn minus h, alpha h, to the power of 1/2. So qn will be equal to qn alpha times h, power of 1/2. So it'll be h naught will be equal to qn naught divided by alpha to the power of 2. And then what else do we need to have? I think that might be it. Oh, we have to define our new flow rate, which we're also given, which would be 0.55 meters cubed per second. So now we can go ahead and define our function, right hand side, the independent variable time, our independent variable will be time, and our dependent variable will be height, which we'll just unpack as h will be equal to vec 0. So now we can define dh dt, which will be equal to qn minus alpha times h to the power of 0.5, and this will all be divided by cross-section area A. So that's nice and easy. We can go ahead and return it now. Return dh dt. We'll put it in brackets so it returns diff. Oh. Now let's see if it worked. Using solve IVP, say Tn will be equal to 1,000 seconds. So as I solve underscore IVP will be equal to, right hand side with the function, T-span will be 0 to T end, and y0 is any, so y0 we can define as, oh, that's our h value, sorry, h naught, and then method will be equal to rad a, and dense output will be equal to true. Sweet, so it's solved. So let's take a look at these values now. So we'll say t plot will be equal to np dot linspace. It's not just random points, and we'll look at 1,000 of them. So we'll go ahead and unpack this now. We can say res equals res x, no, say h plot will be equal to res dot solve at t plot, and then it will return an array, so we want the first index of that array. I don't know how to type that. And now we can go forward and make the plots. So fig equals make underscore subplots. And fig dot add underscore scatter. X will be equal to t plot. Y will be equal to h plot, and let's name it equals, say, I'm going to say solve IVP. So there's our plot. Reaches the steady state a lot faster than we need, so we can change this around. So let's start a look at it. The next thing we want to do is investigate the relationship between this analytical solution and the numerical solution that we attempted to achieve, what I tried to describe earlier. So for that, we need our value of alpha, or a value, which is just the difference between our steady state or initial value of q minus the current value, or vice versa, just the difference between q in and q not. And then we had a parameter a, that was a. We had a parameter k, and that was equal to, I have it here on this iPad, I kind of forgot, see what it was. So it's 2 times h naught to the power of 0.5, all divided by alpha. And then we had tau, and that was just equal to k times a. So now we can go ahead and add another line to our plot and investigate the relationship between the numerical solution and analytical solution. So y will be equal to, like we achieved, it was h naught plus a times k times 1 minus np dot exponent by dot e. This is the negative value of t divided by tau. And t is not defined, we'll do t plot. Fig dot update underscore layout. see, there is pretty good correlation. They branch out a little bit using the two different methods. And if we increase or decrease this difference, so let's say we go bump it up to 0.7. So as you can see, when we increase the change or ramp flow rate, the difference between the approximation and the analytical solution kind of grows over time. Or not grows over time, but grows based on that dependence on the difference between the Q in and Q out, the initial flow rate and the current flow rate. And then our alpha is kind of big, it really limits. So I think we had a 0.1 at one point. And there, you're able to achieve a higher level in the tank. So we can simulate it for more time than t, 200 seconds. And that gives you a better look at the plot. So if you change alpha around, you get more level. And when you change, so let's say I make this 0.50601, you get a better approximation with a smaller ramp size there. So those are our first look at transfer functions and deviation variables. So we'll have more practice and we'll have more time working with these concepts. So stay tuned for that in the rest of this playlist.